Today we're going to talk about Lagrange error bound inaccuracy. This is the last lesson for BC. Now I'm going to skip through some of this jargon, but essentially what we found out, right, is that we can use a Taylor polynomial or a Maclaurin polynomial to figure out the y value or the approximate y value. So this blue line is the actual the actual function, and what I haven't read here is basically like a Taylor function that approximates the y value. And what we're really finding is the error. Okay, now what we found out before is that we can find the exact error, all right? But what we're going to find here is that we're going to use two different rules that will help us find an upper bound for the error. So we're going to use two ways, all right? If we have a series that's it's an alternating series, the error will be no greater than the absolute value of the first unused term. All right, so if they ask you, for example, for a polynomial of degree 4, right, using a Taylor series, then you can use the absolute value of the fifth element in it, if you will. Okay. Now we actually have talked about this in the previous unit. Now, if you have a non-alternating series, then to figure out the error, that can be approximated by using Taylor's inequality theorem, or what they call Lagrange form of the remainder. All right, so this gets pretty heavy on the math, okay, but essentially you are going to need to remember what this formula is, so make sure you write that down. I would write that probably the very first thing on my homework. And just to kind of hit the highlights, and I'm going to go ahead, and you should probably definitely copy this down, okay? And then after I explain everything, or as you do your homework, kind of go back, and all of that really does make more sense once you've done it, right? Now this expression right here, which is the very first part of this formula that I showed you, right, is basically this part right here. All right, that expression represents the first unused term n plus 1 in the Taylor series, okay? And then if we multiply that times the max, which is what they call m in that formula that I just showed you, okay, then that basically is going to give you the error bound. Okay, so there's other things that we talked about, like obviously if we increase the number of terms in the polynomial, we get a more accurate, right? We get a more accurate approximation of the y value. So that's why I said the remainder will decrease. And second, as you move away from the center, right, if the farther you move away from the center on a Taylor series, then the size of our n, or which is kind of the error, will increase. Okay, so now let's go on to the first example, right? So again, please bear with me. Okay, this might take a little while, but it's something we have to do. All right, so if I'm kind of droning on and on about something, you can just fast forward. So let's look at the first one, right? We want to write a third-degree polynomial, Taylor polynomial, for a function f about x is equal to 3. Okay, so this is really nothing new. We've done this before, right? So we're going to call this a polynomial of degree 3. And now we're going to use the Taylor series. And I would kind of encourage you to go back and look at what that is. But you can kind of tell sort of what's going on by what I'm about to write here, right? So we have 5. Okay. The center of n x is equal to 3, okay? This is basically 2x minus 3 to the first power over 1 factorial, if you will. And then we have minus 4x minus 3 square over 2 factorial. So I can look up the formula for Taylor series if you don't remember it. All right, so I'm going to stop there because they just want us to have a degree, third degree, which is, this is degree 3, right? So I'm going to stop there, and they want us to approximate f of 3.2. So what we're doing is that I know the f, whatever this function is, all right, I'm trying to find the y value at 3.2. It's approximately equal to the Taylor polynomial at 3.2. So all I would have to do for this is just basically plug in at 3.2. And then, right, so if I plug in a 3 here, at 3.2, excuse me, that 3.2 minus 3 is 0.2. Let's see. 8.2 squared over 2 factorial, or I can write that. So I'm going to go ahead and simplify from now on. I'm just trying to show you what I'm doing here. So essentially just plug in the 0.2 into the function or the polynomial that I wrote above, and then just go from there, okay? So as you can see, this is what we've done, all right? So now it says the fourth derivative of f, which remember the fourth derivative technically would be part of the unused part, right, of the Taylor polynomial, satisfies an equality that the fourth derivative defined at a is less than or equal to 35 for all x in the interval between 3 and 3.2. Use this information to find a bound for the error found in a, all right? So basically, we're trying to find the error bound here. So what we're going to do here is we're going to use the, notice first of all, this is an alternating series, right? So we can use the first unused term, right? And for us, the first unused term will be this. Remember, the Taylor series says you have the derivative, in this case is going to be my fourth derivative at a, okay? Then I have x minus c being 3 over, in this case, n factorial, which is going to be 4 factorial. And by the way, you could use that formula that I showed you. Let me see this formula, and that actually works out fine too. So you could have used that too. Okay, so now it tells me right here, according to that formula, right? That needs to be less than 35. Okay. So it tells me that my error, or my fourth one, remember, this is like the maximum here. So I'm going to replace that. It says here that it's no bigger than 35. So I'm going to use the biggest it can be. And I'm just going to plug this in my calculator and basically go on with life. Well, actually, I just realized I don't have enough to plug in my calculator. All right, now, there's a reason they tell you this, and they kind of talked about it on the list that I show you that I didn't actually like go over it completely. This 3.2 is what you're going to use here for x. All right, so you're going to basically rewrite all of that, but instead of x, you're going to write a 3.2. So now my remainder, which is basically the error bound, it's going to be less than or equal to 35, 3.2 minus 3. And you're going to see that quite a bit here because, see, on this one, they didn't really tell us. They didn't really just basically spell it out for us. So there were some things that we had to assume on there. So now that's pretty much it, all right? So that's the error bound. So now we're going to, it says find the interval a to b such that a is, okay, so this is what they're trying to say, right? If f of 3.2 was approximately, let's see what they read, that was approximately 5.32933. Okay, so what I'm going to do here is I'm going to subtract my error. Zero, zero, 2, 3, 3. And then on this side, I have basically the same thing. I have 5.32933. But on this one, I'm going to add the error to it. So basically, that's going to give us a boundary of how big and how small this can be and still be accurate. So just subtract that and add that on your calculator, and you get 5.327, 5.332. Okay. Now it says, can f of 3.2 be equal to? Okay, so just look at it, right? Is this number and that interval basically, and that range, and it is. So yeah, it can be. And can 3.2 f of 3.2, can that be equal to 5.334? Notice that's outside this boundary, right? So it's outside of this. So therefore, no, we can't. Okay, so that's that. Now it says estimate sine of 0.5 using the Maclaurin polynomial, and it says so that we can kind of do without. Well, actually, no, we can't. So there's a couple of things we have to do since it doesn't actually tell us what the degree of the Maclaurin polynomial, and this is why the second question says what is the least degree of the polynomial. All right, so what we're gonna do first, okay, is we're gonna decide. Let me see here. All right, so we need to do a couple of things, right? First, I'm going to rewrite the formula so you can kind of see where I'm getting these from. All right, so I'm going to write the formula as, this is what they call the remainder, but this is the error. Well, and then I'm going to write you the formula. So it says, I'm writing way too big. I don't have that much space. I'm going to write it like this. Let's see. Where m is basically what's the maximum the sine function can be. Okay, so we'll talk about that, how to find that. Now, we basically, let's see, do we have enough information? Well, we don't know n. N is what we're looking for, really. Okay, but before we go too far, we can find something, right? And this is kind of easier said than, it's actually easier just to think about it other than writing it, but I'm going to write it. Now, think about it, right? What is the error bound for sine is 1. How do I know that? Well, if I just look at my basic sine function, it goes between -1 and 1 the whole time, right? It never gets any bigger than 1. It never goes below -1. So that's why I said that the absolute value of sine is less than or equal to 1, okay? So what that means for you is that my maximum is going to be equal to 1, okay? So I know what m is going to be. Now the rest, I have to plug it in there, okay? Now, let's see what we know. Okay, so we know the m. We can say the absolute value, this is 1. Now for the next part, I can write the absolute value, so this is 1. I have the absolute value of x. X in my case is 0.5, because that's what we're trying to approximate. And then I'm going to subtract the c. Now, because this is a Maclaurin polynomial, the c is 0. And I'm going to write that all over. Oh, this is n plus 1, so let me not forget about that. Now, at the bottom, I have, well, n plus 1 factorial. Okay? So now, what's going to happen is, what I'm trying to do here is I need this to have a smaller error. This needs to be smaller than this. All right, so I'm going to write it like this. Okay? So here's what I'm going to have to do. Okay, what I'm going to have to do is I'm going to have to go off on this side over here, per se. And by plugging in I'm going to have to just basically grab my calculator. And notice that I'm going to write it without the absolute value, right? Nothing here is going to change really. What I have on the top here is 0.5 to the power of n plus 1 over n plus 1 factorial. So you can write it as a table if you want to put that as y equals and just go n, start with 1 and then 2. Let's see, if I put a 1, this is what I get. So basically my goal here is to get a number smaller. It has to be less than 0.001. As you can tell, I haven't really achieved that yet. So by the fourth one, I get an error that's smaller than 0.001. Okay, so basically I would have to do a polynomial degree 4. So n is equal to 4. It does tell me to estimate. The notes didn't do that, so I'm not either. But basically, let me make sure here. Let's see, n is equal to 4. The least degree. Okay. So what that means is, I guess you have to plug in, let's see. I cannot remember the sine function here. I think it's 2n plus 1. So that's going to be 5. Okay, so it has to be at least degree 4. That's what I'm trying to figure out exactly what they're trying to say. All right, so essentially what we're trying to do here, if you kind of look up your Taylor series for sine, it would basically, or Maclaurin series in this case, you would end up with something like this. So notice that when you actually, and if I will attach notes from the person who created this curriculum, but notice that they went all the way to here, and you might be confused about why. Well, because it says at least degree 4, but this one cannot be degree 4 because it basically skips the powers going odd numbers. So they go from 1 to 3 to 5 to 7 and so on. All right, so I need to at least go to that. All right, and of course you would plug in the 0.5 for x. All right, so let's go ahead and move on now. Example number 3, kind of a weird one, but let's just look at it. Right, it says let P3, which is the third degree Maclaurin polynomial for f. All right, so let P be the third degree Maclaurin polynomial for function f using information from the graph of y is equal to the absolute value of the fourth derivative of x. All right, shown below, show that blah, blah, blah. All right, so basically this right here is the same thing. If you read at the beginning of the notes, that's the same thing as the remainder. Okay, so they're trying to say, give me the remainder. So please don't be confused. I know I didn't talk about it at the beginning, but so that's basically what I'm trying to find. Okay, it basically says that if you have your function minus your approximation, right? Your exact minus approximate, the absolute value of that's going to give you the error. But anyways, that's what they're trying to. So that's what they call the remainder the whole time, right? So to do that, what we're going to have to do here is we're going to use the same formula. Now, so this is a Maclaurin polynomial, all right? So I'm going to write the formula here one more time, okay? So this says this. Okay, let me look it up. Yeah, that's right. And I should have written here a... Alright, so I'm not gonna lie to you fellas. I actually finished the whole video and something got messed up, and then it only recorded about half of what I said. So, which is awesome, especially after I found out that after I was literally thought I was finished, and I tried to press stop, then an error occurred, and apparently it stopped recording after 20 minutes. So, for your sake and for my sake, I'm not gonna rewrite everything, but I want to quickly explain what happened. Okay, now this right here just basically represents the error, or what we call the remainder, right? So the error bound. So on this particular problem, okay, what they're going to do here is I'm using this formula up here. All right, now notice that what I had to use this, basically what I wrote here. I had to use this graph, to figure out where the max would be. Now, because this is centered at 0, okay, notice that I decided that the max that this could be was 15, all right, because it's more accurate in the middle because it's a Maclaurin polynomial that's centered at 0. So as you notice, I just plugged everything into the formula. Notice that I have a 3 plus 1. Now, why did I do that? Because since it asked me for the third degree polynomial, I'm basically going to use 3 plus 1. Okay, the 1 just comes from the formula here. So anyways, after you do all of that and you plug it in your calculator, you find out that this is it, which is less than 1 over 400. Right, so now it kind of leads into the alternating series, which I personally find easier. So remember what I said sort of at the beginning, right? Oh, there it is. Basically, if you have a series that is an alternating, the error will be no greater than the absolute value of the first unused term. All right, so that's actually very useful for this. So what I do in an example like number 4, let's see, on that one right there is the first. Notice that it's asking us. All right, notice that it's asking us to estimate what e to the negative 1/2 is, right? Which is the same thing as this. Now notice that what I use first is this, which you should have memorized. Now, because this is an alternating series, right? So please notice that I actually did that first. So what I know, okay, is that the error is the first unused term, right? Now, my first unused term is I don't really know. So what I did is I took the absolute value of this. So basically I took the absolute value of that and then I wrote it right there. Okay. So notice that this is what I have right here. Let me erase some of this stuff so that you can at least see what's going on. I can put it back in here later. All right. So after that, and then I worry about this. I was actually drawing an arrow. So I was talking about it earlier, but it got deleted. Anyways. So that part right there, I basically have to make sure that that's less than 0.0001. All right, so you can just kind of grab your calculator and start checking, plug in a 1 for n, plug in a 2 for n, plug in a 3, a 4, 5. And once you get to 6, you'll notice that my error is basically going to be, my estimate is going to be accurate up to 4 decimal places. Okay, notice that that's why I underlined those 4 decimal places right here. So what does that mean? Right, what that means is that I'm going to use this series right here, and I'm going to go from 0 to 1 to 2 to 3 to 4, okay? And then I'm going to go to 5, which is what I actually deleted that earlier because I was running out of room, right? So this is the 5th one. The 5th one right here. That's a minus because that's an alternating series. So that's a minus 1/2 to the 5th over 5 factorial. All right, so that's what I have. And then when I do that, now notice I'm not going to go beyond that because I know that's going to give me the estimate accurate to 4 decimal places, which is what I got here. Now, if you put this in the calculator, right, it gives you the exact answer, or a more exact answer, I should say, which is this. Now, notice that this approximation is accurate up to 4 decimal places, and after that, it's not. Okay. So let's go on to example number 5. Is there another example after this? No, I think this. Nope. Nope. This is it. Okay. So, okay. So notice that they're asking us to write the fourth degree polynomial for cosine. All right. Cosine has this series right here. So to write the fourth degree polynomial, all I have to do is just plug in a 0, a 1, a 2, and that's pretty much it. Because by that time I get to my fourth degree polynomial. Okay. Now to approximate, all I have to do is plug in basically a pi over 12 here and here. Okay, which is what I did on this line. And that gives me an approximate answer, which is right there. Now the more accurate answer, if I put it in the calculator, is this. Now on B, it's asking me to use the Lagrange error bound to show that this right here really is just another name for the remainder or the error, right? So when you see that, no, please know that it's the same thing we've been doing. They just wrote it in a different way. I wrote the formula here for you. Okay. Now, the part that is not really expressed directly is, remember, I'm trying to use the Lagrange error to figure out that this is basically accurate or more accurate than 1 over 5,000. Okay. Or the error is less than 1 over 5,000, less than or equal to. So I know the cosine all goes between -1 and 1, all right? Or the absolute value of cosine precisely basically should be less than or equal to 1, all right? So that's going to be my maximum, which is what I circle here. So I'm going to replace that m with a 1, okay? And then after that, I'm just going to plug in a pi over 12 for x, which is what you see me do here, all right? So I'm going to plug all that in and find out that this is the answer, which is indeed less than or equal to 1 over 5,000. Now, on C, kind of different problem, right? So this is kind of a different problem. Still using the same function, all right? We want to use the fourth degree Taylor polynomial. Okay, so we're going to use the fourth degree Taylor polynomial just like we did on the last one, okay? Now we're going to plug in a 0.8 just like we did on the last one, and now it wants us to know to determine the accuracy of the approximation. Now, because this is an alternating series, I can use the knowledge that my error is going to be equal to the absolute value of the first unused term. All right, so my first unused term will be the one that follows this one, which would be when you plug in a 3 for and let me go back to the series. I would basically plug in a 3 for n right there, and that's what that would give me right there. Okay, the absolute value is that. Now to find the interval, you're basically going to add, and let me erase this so I can say it again. You're basically going to add your approximation. All right, this is my approximation, right? That's my approximation, and I'm going to subtract this, which is the error bound, or how accurate it is. So when I subtract, I get that. And then what I do here to get the other side is I grab my approximation and I'm going to add the error, which is what this number is. And that's it. So I went through that really fast. Honestly, I just kind of frustrated that I spent like 30 minutes on it and you didn't get to hear it. So it might be just as well for you though, because I don't have a 50-minute video. So guys, please, if you do have questions about this, make sure and ask. And remember, this is the last section, okay? After that, I will have a test about this because I feel that's just the fair thing to do. And then we're going to get ready for our AP exam. All right, guys, till next time.